Hey, welcome back, students. This video addresses kinetic molecular theory and the nature of gases. And so let's go ahead and begin by making one statement from the very get-go. The kinetic molecular theory, which we call KMT, this only applies to ideal gases. Okay, now keep in mind that ideal gases do not really exist. They're not really real. However, gases in general do tend to follow properties of what we do consider to be ideal gases. And in the next video, we're going to talk about the main difference between ideal gas and real gas. But for right now, we just want to kind of talk about some general characteristics or properties of gases. One of those properties is going to be the following. So gases in general are going to have several things or several properties that we're really interested in. And that's going to be the following. One of them is going to be expansion. A second thing is going to be fluidity. A third is low density. A fourth is compressibility. And the last one is going to be diffusion and effusion. And so we're going to go ahead and explore these one by one. In expansion, what is happening here is that gases in general, if I were to draw us a little container here, gases essentially would be taking up a larger space than, say, a solid or a liquid, because the particles of gases are going to be spread out very far. We already know from the kinetic molecular theory that these particles are in constant motion, that their collisions are elastic, and that the kinetic energy is going to be affected by temperature. But as far as the expansion, these particles, since they are moving quite fast in a straight line constantly, they're going to be spread out and they're going to take up the most space. So expansion essentially is if I were to have one container and I put another container down below, and somehow I were able to put a bridge between these two, and so make a bridge like this, essentially what would happen is that some of these molecules that are already in constant motion here, going in the various different directions that they're going in, eventually some of these particles are going to make their way in this way so that we can start to see some of these particles over here, eventually getting to where you have a situation where you have the same number of particles in one container as you do in the second container. And so this is what we call expansion of the gases. And it's largely because of the kinetic molecular theory telling us that these particles are in constant motion, moving in all directions, okay? And they're really not being attracted to any of the other particles. Now, in a similar sense, fluidity is also another thing that we have to consider. Very similar to the expansion, because these particles do not really attract to other particles, they're able to move right past one another. So one particle going in one direction this way, and another particle moving in the other direction, or this particle moving in the opposite directions, since they are essentially not going to be attracted to one another, they're going to be able to move past one another with very great ease, allowing them to act very much like fluids. So if, for example, if I were to put water in this particular side over here, let's say that this particular side up top here has a lot of water particles, and we'll make these in blue. Essentially, these water particles, if we were to make this little tunnel here a valve and we open the valve, essentially some of this water then will begin to flow into the bottom part, eventually filling up to some degree the chamber in the bottom. And that's because the molecules are able to move right past one another, not going to be attracted to one another, and that's very important in terms of fluidity. The next item here is going to be density. And this, again, is tied to the movement of the particles. And essentially, since these particles are in constant motion, what is going to happen here is that these particles, then, when you put them with molecules or atoms of other substances that are moving slower, in other words, they have a lower kinetic energy, that means that their density is going to be very different than the density of things that are moving a lot slower than they are. So items that have higher kinetic energies are going to have higher densities, especially like in the lab that we did here recently, where we got gas or air and we heated it up with a heat gun. We created that gas to move faster, causing it to have a lighter density than the colder, slower air that is on the outside of the balloon that we created. Okay? And essentially the way that works here is the gas on the inside is going to be moving at a very rapid pace all over the place here, whereas the gases on the outside are going to be moving at a slower pace. And that causes the balloon to rise in the experiment that we conducted. The last two here are compressibility, diffusion, and effusion. And let me go ahead and create a new screen, and I'll explain what those two are. Compressibility is the ability of a gas to essentially be compressed or to have its volume reduced from a larger volume in which it occupies into a smaller volume. So let me provide you two examples. Let's say that I have this container here, and we're going to call this stage 1, or I'll just write the little number 1 here, and we'll create a different scenario over here, and we'll call this stage 2. And so let's pretend that we have approximately these number of particles, and so far we've got 12. So we have 12 particles here of whatever substance or whatever gas. And notice here, because these particles are moving in all kinds of directions, they're going to occupy and spread themselves out all across the area. And we can go ahead and measure the height and the width and figure out the area. And then we can kind of look at it and say, okay, we have certain many particles in this given area, and they're all evenly distributed out. If we compare this to the other side and we try to put in the 12 particles as well in the smaller container, over here to the right, then you can see that the arrangement of these atoms now are a little bit closer together. So that's 9, 10. And so you can see that the distance between the atom here is a lot bigger than the one on the right, where the area between the atoms or the particles is a lot smaller. So what we're talking about when we speak about compressibility, what we're really saying is that the volume of a given sample of gas can be greatly decreased or shortened or compacted relative to an initial larger volume. And that's all this really means, that we can take that volume and make it smaller and still have the same number of particles. The last particular item that we're looking at here is going to be the issue with respect to diffusion and effusion. And so let me explain what that is. All right, so here we have two terms, diffusion and effusion. So it's important that I just briefly tell you what these things are. Diffusion essentially is going to be that mixing of two gases or two particles that's caused because of the random mixing of these two things. So let's say that I had two containers, one container here, and I had another container here, and I joined these two together, and essentially I'm going to open these up through a little valve, connecting them into a larger container. Now, if I were to put everything into the one container, let's say that I have two different colors here. I'm going to have particles that are white, and this one over here, okay? And in this one over here, I'm going to have yellow particles. Okay. If I open these up to the environment and I say, okay, I put one on the other, essentially they're going to start to mix with one another. And that would be called diffusion, because they're mixing together, because of these particles are moving in random directions, and it's just happening naturally. Now, if I ask these particles to go through this little tunnel, let's say I open up this little tunnel on both of these, and let me just draw it back up again. And let's say I have a little hole. If these particles then go through this hole and start coming in here, in the one direction, they start coming over here and eventually mix, what's going to happen then is that this situation is what we call effusion. Now, effusion is going to be when it passes through a little hole, okay? And so let's just write it here. And I'm going to say by effusion, because the effusion here is going to be movement through a tiny little hole, whereas the diffusion is happening inside here as a result of the random movement of the particles. So this is just a very general description of what these different properties of gases are. Keep in mind that there are no ideal gases, but most gases do behave as if they were ideal. In the next couple of lessons, we're going to talk a little bit more about the differences between ideal and real gases.